Imagine a world not so different from our own. A world with vast oceans shimmering under a pale yellow sun, continents carved by flowing rivers, sprawling deltas, a sky thick with clouds, promising rain to nourish the land. Imagine the gentle hum of a planet alive, its atmosphere a warm protective blanket. This world is not a distant exoplanet. This world was Mars. Today, when we gaze upon the red planet, we see a cold, desolate landscape of rust-colored dust and rock, a silent testament to a cataclysmic past. What happened? How could a planet with the ingredients for life transform into the frigid desert we see today? The answer is complex, a tale of planetary evolution. It is a profound lesson in planetary fragility. By studying the demise of Mars, we learn how life thrives on Earth. The clues: a lost magnetic field, a thinning atmosphere, a chilling climate, and vanishing water. Mars died because it lost its protective shield, and with it, the air it breathed. This detective story is also about us. To understand Mars, we follow the evidence etched in its rocks. Uncovering the evidence. The first and most compelling clue that Mars was once different is liquid water. Long before rovers touched Mars, orbiters sent back images that stunned scientists. They revealed features unmistakably familiar to Earth geologists. Vast, meandering channels, dried-up river valleys, some hundreds of miles long. Magnificent deltas at channel mouths, rivers flowed into standing water. Lakes, perhaps even seas. Not squiggles. This was the fossilized circulatory system of a hydrated planet. Our robotic pioneers, Spirit, Opportunity, Curiosity, Perseverance, became field geologists on the ground. They turned orbital suspicions into hard facts by analyzing rock chemistry. Curiosity discovered layers of mudstone, fine sediment settled in calm lakes over millions of years. It found clays and sulfates, minerals that, on Earth, almost exclusively form in water. In Jezero Crater, Perseverance identified organic molecules locked in ancient water-formed rocks, building blocks for life, not proof of life. Decades of orbiters and rovers paint a consistent picture: rivers, lakes, possibly a northern ocean. Mars wasn't briefly damp. It had a hydrological cycle. The water was there. Where did it go? To find out, we must dive to the very center of the planet. Ancient Mars had a molten, churning iron core. That motion, a dynamo, generated a global magnetic field. The field formed an invisible shield, the magnetosphere, deflecting the solar wind. But Mars, smaller than Earth, cooled faster. Its core slowed, and the global field vanished. Exposed to the sun's charged particles, one event triggered a chain reaction. Mars Global Surveyor found magnetized bands in ancient southern highlands, fossilized magnetism. Younger northern plains show no organized magnetism. Massive volcanic regions also lack a global magnetic signature. Conclusion: a field early on, gone by the time younger surfaces formed. NASA's MAVEN watches solar wind interact with Mars's upper atmosphere and measures gas loss. It has observed oxygen and carbon ions being carried away. Today's trickle is a faint echo of violent loss billions of years ago. The death of the core was the first domino that unraveled the atmosphere and Mars's habitability. Next, the great stripping of the air. Once Mars lost its magnetic shield, its atmosphere was defenseless. The solar wind collided with the upper air, a relentless bombardment like a cosmic sandblaster. Gas molecules were knocked away and flung into space. MAVEN found argon is enriched in heavier isotopes, a smoking gun for massive atmospheric escape. Atmospheric pressure keeps water liquid. As pressure fell, Mars crossed water's triple point. Pour water on Mars today, it boils and freezes at once, then escapes as vapor. Thus, riverbeds and deltas are ancient, formed under thicker air and higher pressure. The sky itself disappeared, along with the chance for a blue Mars. With the atmosphere gone, the climate faced a second blow, a deep freeze. Atmospheric stripping drove pressure down, destabilized liquid water, and ended surface habitability. A planet that once might have had rain and lakes became a place where water can't stay liquid, no matter how warm you make the ground. A thick atmosphere acts like a blanket, trapping heat through the greenhouse effect. As the blanket thinned, Mars radiated warmth to space more efficiently. Cooling made CO2 freeze out at the poles, further thinning the air in a vicious cycle. A feedback loop of planetary refrigeration began. Polygon-patterned ground hints at freeze-thaw and near-surface ice. Radar confirmed massive buried ice and glaciers, ancient water entombed. Over hundreds of millions of years, with brief warm spells, the long-term trend was irreversible cooling. Water persisted only as ice, or fleeting vapor, never again as stable surface liquid. So where did all that water go? Into space, into the ground, and into the poles. With thinning air and a deep freeze, early Mars's abundant water had to go somewhere, a multi-pronged vanishing act. Some followed the atmosphere. UV broke H2O. Light hydrogen escaped easily. Oxygen was stripped too. A huge amount seeped down, saturating rocks before freezing into planet-wide permafrost and buried ice. The rest retreated to the poles, massive water ice caps layered with seasonal CO2 frost. These caps hold enough water to cover Mars in a shallow ocean and preserve a climate archive. Answer in 3 parts: blasted into space, frozen underground, locked at the poles. Rivers and lakes didn't just evaporate, the cycle shut down, leaving ghostly echoes beneath red dust. But Mars's story wasn't only slow decay. It was punctuated by violence. Impacts and volcanoes reshaped the course of water and air. Early Mars lived in a chaotic shooting gallery of asteroids and comets. Colossal impacts carved basins like Hellas and Argaea, thousands of kilometers across. Such impacts could strip atmosphere and also temporarily heat the planet. Melted subsurface ice could trigger mega-floods, carving some outflow channels in catastrophic bursts. These created fleeting habitable oases, but were too sporadic to sustain climate. Mars hosts the solar system's largest volcanoes. Olympus Mons rises nearly 3 Everests high. In youth, eruptions outgassed CO2, water vapor and sulfur, replenishing air and warming the surface. As internal heat waned, volcanism slowed and largely ceased billions of years ago. With outgassing shut and solar wind ongoing, loss outpaced gain. The air kept thinning. The quieting of volcanoes was another nail in the coffin of habitability. Next, the climate's thermostat turned the wrong way. A greenhouse effect, reversed. Climate stability hinges on greenhouse gases. On Earth, CO2 acts like a thermostat, trapping heat. Early Mars, thicker air, higher CO2, warmer. Modern Mars, CO2 locked away and frozen, cold. Chemical weathering removed CO2 into minerals. Unlike Earth, Mars lacked long-term plate tectonics to recycle it. Cooling froze CO2 at the poles. Seasonal snow, some trapped permanently. Combined with escape to space, Sequestration drastically reduced atmospheric CO2. The greenhouse weakened, the blanket thinned, heat escaped more easily. Loss of the field was the prime cause. Greenhouse demise was the mechanism, the final domino turning Mars from potentially habitable to the frozen desert we see today. Understanding Mars is like assembling a 4.5 billion-year-old puzzle with many pieces missing. Orbiters map rivers, deltas, volcanoes, and identify water-rich minerals from above. They guide rovers to the most promising sites. Rovers are rolling labs, drilling, zapping, and reading rocks for chemistry and organics. Each sample is ground truth, fixing conditions of water, temperature, and pressure when rocks formed. On Earth, Martian meteorites offer lab-grade views no rover can match. Models test scenarios, thicker atmospheres, active dynamos, higher volcanism, and recreate Mars's evolution. Remote sensing, robotic groundwork, and Earth labs work in concert. MAVEN's escape rates provide critical constraints on atmospheric loss. This interplay of observation, measurement, and theory lets us piece together Mars's epic arc, from life-friendly conditions to a world gone cold. The story of Mars is a cautionary tale. It had water, a protective atmosphere, and energy, then lost them to cosmic physics. We learn magnetic fields shield air, solar wind can strip, geology sustains climate, composition matters. For other worlds, we now ask, size and distance, yes, but also does it have a magnetic field and geologic activity? Habitability can be fleeting. A world can be born wet and die dry. Earth's size, strong field, and plate tectonics help maintain its climate. But climates are not immutable. Mars underscores the fragility of atmospheric balance and why climate stewardship matters. Exploration continues. Mars' sample return may bring clues, even geochemical whispers of past life. Mars may be dead, yet it teaches us. Its rocks and dust tell stories that help us protect our own living world.